All right, we're back with one more video. So if you're back for more fun, I don't really know where to put myself. We're going to go right there for now. So if we think about this example, if you're here, it means you've either wanted to watch it before you started the practice or you've started practicing and you just realize you don't know what's happening. So we have a 1.8 meter long bar and it's attached to a wall by a hinge and supported by rope as shown. And so the reason this is a bit odd is because really when we resolve our force vectors into components, we're going to see that this tension can be broken into two components. We can think about this perpendicular component and then this parallel component, so T parallel. And then in the same way, let's do green, force gravitational vector here, which would be straight down, Fg, for the beam, could also be resolved into vectors. So let me go to black here. So this would be a component. If we go 90 degrees perpendicular to the surface, this would be Fg perpendicular. And then in the parallel direction here, down the beam, we would have Fg parallel. So it looks a bit messy. I'm going to actually move Fg over here so that I can get him out of the way. So Fg was here. Remember, this is just normal hypotenuse. And then we have Fg parallel going down here as one other side of my triangle. So the nice thing about drawing this as the triangle is then we can see that, oh, this tension perpendicular has to be equal to Fg perpendicular. And then Fg parallel probably going to be equal to tension parallel, which means that we can make some claims about tension and Fg using this 32-degree angle. So this one starts out just like before with torque clockwise equals torque counterclockwise. That's always a place to start. Literally just write that, just like you write F equals ma, and you probably got a point on a free response. Now in the clockwise direction for this system, we would need to think about Fg perpendicular applying a clockwise torque, and that's going to be opposed in the counterclockwise direction by tension perpendicular. So we would have Fg perpendicular times distance 1, where this distance is distance 1, d1 is going to be half of 1.8, and then that would be equal to tension perpendicular times d2, where d2 is the full length, the 1.8 meters. So my tension perpendicular is going to be Fg perpendicular times d1 divided by d2. And I guess we should go back to the problem. They want us to find the tension in the rope. Every people hanging things and moving things, think about engineering and stuff, we always need to know about the rope so that we can know if we can lift whatever we're trying to lift, whether we're hanging a sign or whether we're just pulling up like a stack of bricks or whatever. And so those of you who are future engineers, this is very, very helpful stuff. But if I can find a component of the tension, then I can use my trig functions to find the overall tension itself, in theory. So thinking about Fg perpendicular, if you're still struggling with finding different components of your triangles, we are given that Fg is equal to 12 kilograms times 10, so that would be 120 newtons, mass times gravity. And so checking my clock so I don't get the bell ringing on me again. We're still before school here. So Fg would be 120 newtons, which means that Fg perpendicular would be my 120 newtons. This angle is given us 32 degrees. That is talking about the angle of inclination here, which would be the same angle as the angle between Fg parallel and Fg perpendicular. We've done this previously with some examples, and if you need to go back and think about inclined planes and how that geometric relationships worked out, you can check out that video. But here we can just say that this would be Fg times if this is my angle 32, then I can use the cosine to find this adjacent side. So this would be the Fg cosine of 32, which means I would be doing 120 times the cosine of 32, making sure we're in degree mode like always, which means Fg perpendicular is equal to 101.76 newtons. So bringing that over here, I can find tension perpendicular is equal to 101.76 newtons times d1, being 0.9 meters, divided by my total distance, 1.8 meters, which gives me an answer of a number. So we'd have 101.76 times 0.9 divided by 1.8. So that's 50.8 newtons. Okay, now that we know that that's 50.8 newtons, we can find our tension by thinking about the overall vector here. We just found this vector, which is 50.8 newtons. And so if we know that, and we know this angle, which is, you guessed it, also 32 degrees, then we can solve for tension by doing tension is equal to tension perpendicular divided by the cosine of 32 degrees, which is equal to, we would do 50.8 divided by the cosine of 32. So that's going to be about 60 or 59.90 newtons. So that is how we would do that. Now, there is a shortcut we could have actually done because these angles are the same, but if you follow this procedure, you can work it out with any angles, assuming that the angles are, you can use it with any angle. But this one was kind of nice because the angles were identical, based on the fact that if you kind of create your system, you can compare the two and work that one, the top one out to 32 degrees. So hopefully that's helpful. In the bottom one, I'm going to jump over to the filled in version of the notes here. We would actually have to do an additional step. So let me show you what that looks like. And these are posted online if you want to kind of work it out and then check yourself. So here we have a gravitational force vector that's straight down. And so when I divide that into its components, then we would have a component here, FG perpendicular, that would be opposing tension perpendicular, just like before. So here I would have a 50-degree angle, but then my other angle between FG2 and FG perpendicular would actually be 40 degrees, since we would then be solving kind of backwards for that lower angle. So that's what I'm meaning about you have to watch your angles and make sure you're keeping everything straight. So if you need additional help, I would work this example out and then check it here. And then try a couple of the 3.3 and see how you do. Remember, the answers are all on there and you're just doing the odds. So hopefully this is helpful, and if not, we'll try them together in class.